matrix of SOG plus 1, and we denote it by small ag, or it can also be a CG, which is the minimal, the closure of the minimal orbit of SPG for physicists, or SP2G for mathematicians. It's SP2G, or it can be a non-normal slice MG, whose normalization is C2G. Okay. So later I will see the I will specify the polynomial ring of this. So actually the ring of this, or you can also define MG as the spy of so basically when we take the ring of C2G, we denote that by x1, y1, and dot xg, yg, and then we take away the degree 1 generators, the degree 1. So for example, the M2 is basically the ring of M2 will be x squared, xy, y squared, and x cubed, x squared y, xy squared, and y cubed. You will see all those generators, they are generating the polynomials with degree larger or equals to 2.
Yeah.
And so they can be all be encoded in a combinatoric way in a quiver. So I will just write down the rule for now, and I'm going to explain how what is this response. So firstly, so locally, if a quiver contains n copies.
I just want to point out, this doesn't matter for you, I'm sure, but I want to point out that this set takeaway is not mathematically correct on that second.
So this one.
Yeah, that's not mathematically correct, but it doesn't really matter. Everybody knows what you mean.
Yeah. Yes.
Yeah. Also, yeah, we have complaints about it too. It doesn't listen.
Yeah,
Yes,
it's
so
for me, it's fine, but just no one should think that it's mathematically correct.
Sure. So then we're gonna write this. This passive.
I would maybe superscripted with a just take the polynomial ring, superscripted with a greater than equal to 2. I would do something like that. Just to indicate, you've got a greater thing.
Yeah, that would be one. Okay, that would be one third option. How to do it would be. We could do C plus the stuff, the whole ring and degrees greater than equal to 2. So that would be an option.
So
That would be mathematically correct.
like this.
I would have to say, would you do a superscript or
I would do a super, but it doesn't matter.
but then you have to add a C.
Constant function.
Then you need to take the C plus this whole thing.
So
Yeah.
At the beginning, put C plus,
It's whenever your remaining rings.
Yeah.
On top, yeah.
C plus that.
You could say the green is like the one.
Yeah.
Right.
Is this fine?
Yeah, that's nice and compact. Hard to understand.
That bothers me a little bit. Because I mean, not everything has a degree, right? They're inhomogeneous in general, these polynomials, but yes, I mean, I guess we know what that means.
But maybe just a further question, does this space have a like sort of more intrinsic geometric interpretation?
geometry interpretation.
Yeah, this is
Actually, I will see. Yeah. Later I will explain when I finishing the rule, so you can kind of you can think of. I don't know if it's a geometry. So a more physical interpretation is like you can think of you are trying to identify different object, and that's when this thing.
So
You're taking the
maybe not the day, you don't write day, do you? Just greater than or equal to 2. Do you write day?
I wouldn't put deck now, but I think it's put greater.
So maybe get rid of the dig, just greater than or equal to 2.
this.
Just delete the dig, just say greater than or equal to 2, that's better.
That is.
Okay, perfect.
And yeah, so in the quiver language, it's basically, so every time I will explain this QADE. So what I mean by QADE,
But we'll do the brackets to
uh,
all the C or things.
The,
Because spec is taking square brackets.
yeah, you could put round brackets for the spec. That's a good idea. Good.
So sorry, just to interrupt again, my thought is that that looks vaguely like something to do with the Segre effect. Is
yeah,
but anyway, yeah.
so we can discuss.
Yes.
Yeah, this is good like this, yeah, it's good.
So what I mean, QADE is a balanced thinking quiver of either A type or D type or E type. So if I see Q A1, it will looks like this, or we have QD2, QD4, it will looks like just a fun thinking quiver with the corresponding thinking loop. Oh. And every time in your quiver locally, you have n copies of this. What I mean n copies is, for example, the n copies of QA1 is just like n, and so we just increase the rank of the node by n times. And the corresponding transition will gives you expression. Looks like this. So which means you are taking m copies of the QADE, and you shrink it to a node with a adjoint representation attached to it. And then the transition will be ADE singularity. And for the second rule, is that when you locally have something that looks like this, so a two node N1 and 2, and the edge, there are G+1, the fundamental edges in between. And then you can have a transition into something that looks like this. It's G. One minus m and 2 minus m, and there are G +1 edges in between. Here is G minus 1, G minus 1. And also the will connecting to the background. So here you can think of you are subtracting, let me show them. Here you can think of you as subtract something like this. And here you can think of you as subtract m copies of QADE from your.
What's the class of quivers you're studying?
Negative variety with or unitary quiver with possibly multiloops.
Okay. That's the under the classification.
Yeah, I should see. Sorry. And the last possibility will be, so locally, it looks like node of n with G loops attached to it. Within the transition can be either CG. So the next phase will be M, G, and mirrors out. And there are 2G minus 2 edges connecting between. And it can be CG. if n equals to 2m, and this mg if n not equals to 2m. So what I mean here is that if you start with a random quiver, like I give you some, so because the quiver we are starting it will locally, let's see. So locally it will looks like a node of n with a possible like random number of loops, and also it can connect into different edges. So that's how your quiver locally looks like. Okay. And to apply this rule, so you just skim over the whole quiver and you find like did it have any pattern looks like something contained in the rule, and then you apply the algorithm. So I will give you an example.
Okay, go ahead. Got that already. Right.
So for example, so I will let's look at the Higgs branch of the quiver 1, 2 is a loop. And the Higgs branch actually we know it's a 2A1 instanton, modular space of 2A1 instanton. And if we apply the rule, so we know at the bottom,
That's not good.
well,
Oh, okay.
yeah, that's the Higgs branch of it. 2A1 instanton. So as we can see here, there are so we have a node 2 is a loop, so we can apply loop C, which will give us quiver looks like this. Like Lucy is splitting the node into 2 nodes, and here because the G equal to 1, we can see there's nothing, there's no edges connecting to. And also we can apply loop B. Or actually, equivalently is rule A. So rule B and rule A, if we are only considering G equal to 1, they will be. Rule B will be a special case for A1. And here we will have. Sorry, no, it's only.
So let's make sure that we all understand though what all this information is on this page here. So so you're starting with a unitary quiver, which you can also think of as, you know, just a quiver with a dimension vector, a graph and dimension vector.
Yes. Yes.
Now you're taking this Higgs branch associative, which is also called a Nakajima probability, right? And now you're taking a minimal leaf closure, which is now 0 in there, right?
Indeed.
And you're taking the slice to it.
Yes.
And the arrow is labeled with the minimal leaf closure that you took.
Indeed.
And then the thing on the right is the formal slice to that at any point of the minimal leaf closure, a minimal leaf, not the closure. At any point of the minimal leaf itself, we have that as a slice.
Yeah.
So the singularity at the boundary is this AD or AG or whatever,
Indeed.
and then
So-
the singularities along the leaf in the slice direction are the thing on the right of the arrow. Does that make sense, everybody?
So you can think of like this as your whole stratification of your the symplectic leaves of your quiverarity, and this Q at the bottom will be the quiver you are starting with, and here is a Q prime, which is the slice to the top will be the quiver after the transition conquer.
What are all of those graphs that you?
Here,
Yeah,
there is an example that demonstrates this
Yeah.
algorithm.
but what do they mean?
What do they mean?
Yeah.
So maybe let me finish the rule and then.
So maybe we should make sure that everybody understands what this this Hasse diagram is, right? Maybe everybody here
Ah.
does. But does everybody know what the Hasse diagram is? I think my student here might not know. So it's, the point is that, the point is there's some stratification of
Yeah,
so the quiver variety by some things that are called leaves. So there's a disjoint union of things that are called leaves. And for each leaf, we put a vertex on this diagram. And then we put edges to say that the closure of one leaf contains another one. So the small leaves at the bottom, the bigger ones at the top. Right? And then that you're labeling these edges by what they call the slice. So if you have a small leaf and a bigger leaf that has it on its boundary, and you take the slice inside of the bigger leaf to a point of that small leaf, and that's what you put on that edge. So of course, if the small leaf is just a point, then it's just a singularity of the larger leaf. But if that small leaf is bigger than a point, you take a point of that and you take a slice to the leaf there. Does that make sense? A little bit? We'll probably
So,
need
like,
to
we are going,
go
so
into
so
my-
basically we will draw like the Hasse diagram looks like this, it's linear and so at the bottom you are at the most singular point, and when you go up, your singularity, the degree of your dimension of your singularity decrease, and when you reach the top, it will be the smooth side. Okay.
So basically, at the moment, you're gonna have to accept this right board as some formal rules for how to generate this whole diagram from the original. So just some combinatorial rules to generate the whole diagram from the original thing. But maybe later we'll see some examples so you can understand better what these diagrams look like.
Sure. Is it always a linear diagram? So
It's not always linear.
yeah.
It can be like,
Yeah, definitely not.
it can be many different. Actually, already here you can see, because I didn't specify the value of m here. So it can be many different directions. So as long as m is a lot smaller than 1 and 2.
Another thing to say is that these are the three rules you can do. So basically, what are these three rules doing? You're taking your original quiver. And now you're looking for the minimal leaves. That's the way this procedure always works. And so the minimal leaves are, there's three different types given by A, B, and C. But if you have multiple minimal leaves, then necessarily that bottom will have more than one valence. The valence of that bottom vertex will be the number of minimal leaves. So in order to have just a line, you have to have a unique minimal leaf. Every time a unique thing you can do, and as Deshuo points out, if that unique thing you can do is this type C, right?
Yeah.
Or is it, yeah, type C, then eventually if n is bigger than 2 or whatever, you're gonna get higher valence later on. That makes sense? Or even already at the bottom, you're gonna get more than 1 at the bottom if the n is bigger than 2, right? Because you have n equal to 2m and n not equal to 2m, right? So we have a choice of m already for that bottom thing. Yeah, does that make sense?
Yeah, and it has to be three. If n is two, you have one.
Yeah, it's 2.
Yeah, right, so if n is bigger than 2, sorry, if n is bigger than 2, then already you have more than one choice of m for the bottom things. To have uniquely, have to be only one of these types available in the graph, and if it's type C, n is 2.
Also for type B. Well, the bonus choices of three.
So all ABC, we can all have different choices.
Oh, right, okay.
M to, yeah, M to C, so M
Well, that's right, they all have choice of m, sorry, yeah.
smaller or equals to N, and here M is smaller or equal to minimum of than 1.
Sorry, yeah.
And then here is M is smaller or equals to.
There's non-zero, right?
Yeah, they have to be
Greater or equal to
larger than 0.
Right, I see. But for the last one, we don't want m to equal n either.
Sure.
N divided by 2. You have to-
Yes, but we can have they will identify.
No.
If there.
By 2, yeah. Has to be less than,
That's all equals to 2.
yeah. Because then, if
Yeah,
you have
yeah, otherwise it will be identified with a smaller.
if you have 4, 1, 3, and 3.
Ah, yes, okay,
Yes.
thank you, yeah, okay, that's better, yeah. So anyway, now my corrected statement is. To have a unique leaf, you have to have only one of A, B, or C available and only one value of N possible. There, that's the correct thing. Right.
So, yeah, so any more questions about these three rules?
You're working on Higgs branches.
The Higgs branches. So Coulomb branches, of course, is a different rule, but yeah, very similar. What's this? Okay. So then let me finish this example. So here we can see a rule C can be applied on this node, and after the rule C, we can continue to apply rule B. But they will give us two different directions. So because we have two A line here. Or actually here we can also see it's rule A. Because locally we can see we can treat this part as a A1 or as a special case for B when A equals to G equal to 1. Okay. So after applying the rule A or rule B, and we're going to end up with so still 1, 1 with the rule this point. We will have two loops here, and also on this side. One with a loop, one with two loops, and also for this two, we continue to apply the rule.
I also want to point out that these rules that we have on the board, this will eventually appear. Hopefully in my paper with Win, but these rules can all be derived from the representation theory of the quiver as well. So you can think about these leaves in terms of decomposition of the representation, and then you can derive the rule from that. It's just actually what's called the local quiver.
Yes.
So you can do this. You can do this more generally than this is the rules for the minimal leaves, so you can derive such rules for any leaf as well. It's just
So what holds you at the moment? From the release?
oh, we haven't finished there. I mean, this part I guess is okay, but like for example, I mean, I just at a time I guess haven't I have to edit it, and then there was also an issue which we haven't completely resolved. And as we were wanting to say something about when the leaf is normal.
Nice.
So if you want to fully classify when a leaf closure, I mean, not the leaf itself is obviously normal. When the leaf closures are normal, if you want to classify that, we haven't completely classified when that happens.
I see. So yeah, so maybe one more comments about the number of loops. So because here I didn't include the loops, but the basic rule is like we can so all the loops on the node of U1. So because it's just gives you a free module of C2, so we just carry it into the next step. We don't care about it, but when we apply the algorithm, we just keep it here. This is why here is a two loop on this node 1, because we are subtracting a quiver looks like this, and this guy will give you one with one loop, and if we add some more loops on it, for example, here is G1 loop, here is G2 loop, and overall we will have a node 1 with G1 plus G2 plus 1 loops.
So you also expect the result of graph purchasing, that the leaf closures is normal. Is normal only if the last slice is normal. I think they call it Gaussian of one.
So I think, yeah. So the top leaf have to be normal
The top leaf has to be normal.
if you want it to be normal, and if the top leaf is not normal, it's necessarily not normal. But I don't know if this is sufficient classification.
Right,
So Carpocci improved it for input and output of Gaussian, right? The question is whether we can extend.
so they proved that a leaf closure is normal if and only if. What is true?
The last slice.
The top slice.
The top slice.
So
So
this
the
one.
subnormal, the sub-regular, whatever.
Not necessarily. You're talking about the heat. Doesn't have to be the.
Ah. Oh, okay, so you're saying that the whole leaf closure is normal if and only if already the slice to
To the
all of the next to biggest, next largest leaves is normal. Okay,
for example, is a leap
so
here.
one direction is obvious, if the other direction is a theorem, then okay, which is easy to say for the nil quadrant.
Yeah. So if you want this leaf to be normal, and then all these slices connecting to it have to be normal.
Yeah, that's obvious that there has to be, but then they say it's sufficient. Okay, so then I don't know. Then if this is true for the quiver case, at the moment.
So
Yeah, I think about it.
We're kind of assuming this that the both actually saying to be done to the theory.
So after we apply the rule, if we summarize the Hudson diagram, it will look like this. So basically it's a diamond of A1 with a A1 also at the bottom. But the thing is, like, we know this Hudson diagram is not the full story of two A1 instanton, because the Hudson diagram for two A1 instanton is actually looks like this. So the top slice is A1 and the middle slice is the union of two A1. So with the S2 action commuting the two components, and then the bottom slice is A. So there is a missing ingredient in this. If you only look at how the geometry locally, how the slice locally looks like, so this is the correct algorithm. But then if we want to know the global structure of the Hudson diagram, we need to include more ingredients into this algorithm. And to cure this, so we have something called, we introduce something called a decoration.
What was this thing with the A1 union A1 supposed to?
Yeah.
supposed to be?
So because
What was the A1 union A1 supposed to be?
so because we know that because we are studying the Higgs branch of this quiver.
Yeah.
And we know the Higgs branch of this quiver is a 2A1 instanton moduli space.
Yeah.
And we know the modular space of 2A1 instanton should be this one instead of this one.
Right. Ah.
So which
How
tells us
How do you know this?
Huh?
How do you know this?
this one.
Yeah, I mean, how can you tell between the two?
So locally I cannot tell, but globally,
Why do you say you know this?
Oh, I see. You're saying that the actual Hudson diagram is the one on the right, but the one on the left is what you get using this algorithm.
yeah. So this is derived.
Can you apply?
So this is derived from the Coulomb branch. Actually, you have a Coulomb branch quiver, and from that quiver you can see the structures here.
Okay, how is this known on the Coulomb branch?
Well,
I don't think. Give me one test which will choose between one and the other.
I mean, I can tell you from the algorithm, and you probably know this, I'm sure you know this already, how you can add into the algorithm the
Yeah.
fact that it's the right hand thing, not the left hand thing. I guess you see this, right? Like if you just modify the algorithm,
Yes.
then you can make sure that you get the correct thing.
Indeed.
But so the algorithm that you have gives the right one, not the left.
Sure, yeah, I mean, we haven't written it as an algorithm per se yet, we just written the classification of the minimal leaves and what the closure and what the slice is. But yeah, you can turn it into an algorithm that gives you the.
Okay.
But it's just a question of whether you're keeping track of which of these are the same leaf and which are not.
Yes.
So the fact is that if you don't pay attention to that, then you get the thing on the left, but then if you pay attention to it and you see that those two vertices are actually the same leaf, then it's actually the thing on the right. So the leaves are labeled by decomposition type in terms of the original quiver. Not in terms of the quivers you get subsequently, so that's the difference. So you can get in the subsequent quiver, when after you're taking these local slices, you may have two different A, B, or C, or two different values of M, whatever you can apply. But then when you go back to the original quiver, you see that it's the same decomposition, so it's the same leaf. So here in the original quiver, we had only two vertices, so there's not as many choices, for example, of decomposition as there is in this bigger quiver you get later on.
I see.
And that's of course one of the primary ways you can get non-normal slices. So there's either that or this part C. Those are the two ways you could get it.
Let's see.
So this part C one, this has so of these rules A, B, and C, the only one that gives you something non-normal is that C with the MG, right? That's non-normal. But of course, then these conditions are telling you whether each component of the slice is normal or not. In general, you can have many components meeting. So if you have more than one component meeting at a point, then the normalization just separates the components. So it's normal if only if there's a single component and it's not of this type CMG.
So for example, this part, this DB is non-normal because it's union of A1, union A1 is normal.
Right, exactly. Any union of more than one component will be non-normal. The normalization just makes the components disjoint and normalizes each component. They're not already normal. Right. Is that clear to everybody? Is there any questions about that?
So the expanded diagram on the left is like a picture of a partial normalization, when you sort of normalize the, you don't normalize these components, but you extrapolate these.
That's a good question, actually. So I mean, the algorithm is only going to give you non-normal slices. If you're not paying attention to which leaves are the same, then this diagram on the left will have only normal slices except for these MG ones. But even in the case when there is no MGs, I'm not sure if that corresponds to the Hasse diagram, literally of the normalization of the original thing. But I don't know. But the thing is that the original thing itself is normal, actually. Any quiver variety is normal already. It's just that the leaf closures aren't normal. So you have to already say what you mean by taking normalizations. It can only literally make sense to take every leaf closure, not necessarily a minimal one, and take its normalization. So I'm not sure in what sense one can recover the Hasse diagram of each of those normalizations from this thing on the left that I haven't thought of yet. Because it's a little bit weird, right? Like every quiver variety, every Higgs branch of a quiver, of a unitary quiver, is normal. So when we're talking about this like Cross-Prochézy result, that is talking about, from the quiver point of view, it only makes sense to talk about leaf closures, whether the leaf closure is normal or not. And Amihai says we should be able to detect it by looking at the top slice to that leaf closure, but we haven't checked this. Does it make sense? And the same is true for nilpotent orbits in the sense that the whole nilpotent cone is always normal. Yeah, it's a complete intersection, in fact. Yep. Right, okay.
Yeah, so one combinatorial way to keep track of this piece of information is to add something called calibration, like it's more modified to the rule. So instead of just seeing this, we actually every time we apply the rule. So we add two different components, like a blue circle, to decorate them. So actually, this idea also comes from inertially comes from the Coulomb branch algorithm. But here we continue to apply it to the Higgs branch side. So what this declaration tells you? So actually, the declaration will be actually it originated from a non-trivial or well action of your original. So for example here. So for the root C, you have a UN here, and the well action of this UN, they are non-trivially acting on this the subgroup of UM times the mass. So we have to keep track of this non-trivial well action of SM. And one way to do it is to just add the declaration. So as an example here, so instead of just this quiver, we need to add the declaration to it. So and when we're doing subtraction, we identify like the components with the same declaration. So for example here, we see the root B can be applied to the top alpha A1 quiver or to the bottom two nodes. But because they have they look the same and also they have the same declaration, so identify them as a union. And we see there is a S2 action.
Why are you doing this?
So because this declaration is an indication of non-trivial well the well S2 symmetry, and because this well so if speaking physically because this S2 is belong to the gauge group and they are commuting these two components, and so we should expect it resulting in the same leaf. It should not be a different. It shouldn't be a two different leaves because this S2 is a well symmetry. Is a gauge symmetry commuting the two components. And the gauge symmetry should not result in two different phases.
What does this imply for the slice?
So for the slice, it will necessarily means these two components, these two leaves have to be one. We don't result into two different phases.
So now you're answering the question.
Yes. 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 So that's why here it's no longer two different directions, but it's just one direction.
Because of the symmetry, you're saying.
Because of this S2 symmetry, yes.
Which is similar to what you said.
Yeah.
Right.
Indeed.
That's right. I'm not sure off the top of my head whether it's equivalent.
Yeah.
Definitely it's true. One direction is true. If you have a symmetry, then you're going to get the same lead.
Yeah.
I'm not sure if that's sufficient in general, but it's definitely sufficient in general to ask whether the decompositions define the same decomposition of the original quiver. Then will tell you if and only if they're the same lead.
And actually, these two nodes, you can think of they are exactly a graphic representation of the normalizer of this U1 square of the Catan within the U2.
Ah, oh, that's interesting. Okay, this is something I haven't thought about. Okay, I would like to hear more about that, but go ahead.
So in general, so because root C is the best way to demonstrate this thing, and if here we have a node of n instead of S2, in the end we will recover because if you continue to apply this rule, so in the end what you get will be a bunch of U1.
What is this n that you like?
Normalizer.
Normalize.
Normalizer.
Is
yeah, so this is
also
also
the
go
common notation?
capital N.
I think what you want to say is that this is the normalizer of U1 squared inside D2.
Yes. I see this somewhere.
Yeah, I think that's correct, yes.
Okay.
That's correct, it's.
Okay, and
Wait, sorry, it's not correct.
okay.
You meant that modulo.
Yes.
U2 squared.
I need to modular.
This is probably what you meant to say.
Yeah, I need to modular U1.
You could take the quotient.
Yes.
So obviously the group itself normalizes itself.
Yes.
But this is what's called the Weil group.
So, but do we have a like a better notation for the modular the group itself?
Normalizer of H modulo H. In this case, it's the Weil group, right? But in
Yeah.
general, I
Yeah.
don't have the notation for this.
Okay.
It's a natural thing to do, though, of course.
Yeah.
Maybe there is a notation in like, maybe these people doing working on these nilpotent orbit closures or whatever have some notation for this.
We call it to reduce the normalizer.
Okay, yeah, yeah, I don't know if I've heard this term before, but it's a natural thing to do.
So actually, the union is one possible effect of this decoration. So the decoration can be resulting to two different phenomena in the quiver in the Higgs diagram. So the first one you already see here, it turns two different leaves becomes one. There's a natural S2 in it, and this S2 will make these two distinguished leaves no longer distinguished. It will glue them into one. And another, so let's see, declaration. So what is imply? So firstly, it will imply the union of leaves, and also the union of slices with action symmetry. Also, here I should put slice, because what I really care is the information of the slice. And two, the second one, it can be resulting. So if we start from ADE singularity, it can be modified to the corresponding C G or singularity. So for example, what I mean here is that when you have I will make a table of all this stuff. So do you still need a rule? I can erase it.
I took a picture, so hopefully, if we need it again, I can pull it up.
So just leave rule C here.
Also have the cameras rolling.
Yes.
By the way, if any of you don't know, or any of your colleagues don't know, we are videoing, we're taking 2 videos of all of these talks. So I mean, anybody who wants to get access to a video, tell me if you don't know how.
So again, singularity will be that we draw a Upon quiver of AN dot 1 1. Since I think that should not join it. There are n node here, and in total there are n plus 1 node for AN. So it's a group for AN, and also for DN. It's like this. And for E-type, I will not draw E-type here, but that's just demonstrated on A and B. So, and also I need to draw D4. Maybe I should also draw E6. I will draw up to E6, and then of course we have E7, E8. And also the decoration, how the decoration going to change the singularity. So for example, for this AN, we can somehow, actually I draw it in a very bad way, which I should not. I should draw it in this way. So 1, 1, 1. I should draw it as a ring. So and we come to the decorations on these two large components. And this will give us and if we fold this quiver according to the decoration, so it gives us a thinking quiver of type C. Okay. So here is AN, and here is capital C. Should this be Cn over 2 plus 1? Maybe I better wrote A
needs to be even.
A to N 2N plus 1. There's A to N plus 1. And then here you see
Maybe you want to.
and then if we subtract this quiver, we actually call this corresponding slice as the secant, capital C. And also there's a special case for D4. So for D4, we can also put a 3 decoration here. And we put 4 according to the decoration. have a G2 quiver, and the corresponding slice is called the capital G2. Okay. And you may ask, so what if we add more decoration? Like for example here, so if D4, we add one more decoration here, so will this result in a new slice? Actually, the answer is no. So because we should really think of this as a automorphism on the finite thinking diagram instead of affine thinking diagram. So the three of them and the fourth. So if you put another decoration here, actually it will give us the same G2 slice. This S4 on the affine thinking diagram will be reduced to a S3 on the finite thinking diagram.
So when you circle these in blue.
Yeah.
What do you mean now?
Decoration. So they can be your result. For example, here, if I do something looks like 1, 2, 2 is a loop, and then when I apply this algorithm, the thing I get will be 1, 2. Sorry, what I mean is 1 will be a D4 with two of the U1 node decorated. And then instead of and then if I continue to apply the rule, so if I ignore, so here is A1, and if I ignore the decoration, what I'm going to get should be a D4. So however, this is not so correct. So what we should really get is a capital T3.
I see.
Yeah. So this can be checked through the dynamical vowel groups of the slice. So because the dynamical vowel group of D4 is necessarily the vowel group of D4, but the dynamical vowel group of the slice C3 should be the vowel group of B3. The same logic if you have 1, 2, 3 here instead of this one. And this is actually an example I will show you.
So I just want to make sure I've understood the statements you're making then. So in the presence of this additional symmetry, you're saying that the slice, which is a D4 slice, has some additional symmetry.
Yes.
And the symmetry means that instead of having two different D4 slices, we have
a single D4 slice with the S2 intrinsic symmetry. It's the expression. So basically, in summary, so now we introduce the decoration to the rules, and so when you apply the rules, you will meet the slices. You will meet the local component with content decoration, and in this case, the information of the transition have to be is no longer the original one. We have to consider the symmetry carried by the decoration. So that's why we will have this type of modification.
But actually there's two different rules that we can apply here. So we should be getting two different D4 slices.
Yes, so there's only one, right? So because this is the D4, and what we do is like we subtract this D4 according to rule 1. But D4 was subtracted, it have two decoration on top of it. And so we know it's D4 with the S2 symmetry. And the D4 with the S2 symmetry is C3.
But are you saying that we instead of getting D4 union D4? Just
No, here we will not have D4 union D4 because there's only one D4 here. And here it's because here is A1 union A1 because there are two different A1 components. But here we only have one D4.
So it's just one D4, but this additional symmetry.
Yeah. So yes. So maybe a more a good example to illustrate like both the union and the symmetry is actually
okay, so your point is that there is only one rule we can apply, the one D4, but when we apply it and we have some symmetry on there, then that is telling us that there would be a different Namikawa group than the expected one.
Yes,
The slice is still the D4. The Hata diagram hasn't changed any. There's no correction needs to be done. The Hata diagram is additional information
yes,
about the Namikawa group of this singularity.
yes. So I will give you two nice examples here. So one is 1, 2, 3. So if you apply the rule, so the first step, we'll go to 1, 2, 1 with a loop, 2 with a loop, and they are all decorated.
The Namikawa group, by the way, maybe not everybody knows what it is, but the Namikawa group is mathematically some difference, telling you the differences between the resolution of singularities, or the best you can do to resolve if you can't actually resolve it in a Krepin way. So the Krepin resolution of singularities, or the best approximation of that, is different between the behavior of that and of the original singularity that's measured by this value, something like a Galois group. But in terms of the singularity, this Namikawa group is telling you something about the codimension 2 leaves. So the biggest leaves are not open. And for each leaf, you get a factor of this group, and you just take a product over all of the codimension 2 leaves of these factors. And the factors, the singularities that you can get to the codimension 2 leaf have to be ADE singularity. Those are the only possible surface singularities which are symplectic. But the groups you can get are not just AGE groups, you can also get the non-symbolic ones. So what Deshuo is saying is that in this situation, for this minimal leaf here, if you put it back into the original quiver and you get some leaf in there, which is of some dimension, then it's going to have a Namikawa group. Its closure, it's going to have a Namikawa group, which is the C3 instead of a D4 this way. Does it make sense? So some additional information. Is that right, Deshuo? That corresponds to what's running?
Yeah, so actually give you more physical not that physical comments. Is like for each gate node here, they should carry the Fi term, and this S2 is symmetry that actually identifies these two Fi term. So in this case, if you want to turn on the Fi term in this node, you have to turn the Fi term on this node with the same value.
Right. These Fi terms are the parameters for the resolution of singularities or the deformation.
Yes, the parameter for the.
And so that's exactly so what's happening here.
Yeah.
I didn't say exactly what the difference in behavior is, but the difference in behavior between the resolution of singularity and the original thing is that in some deformations become identified. All right.
So one example is a quiver, the Higgs branch of the quiver 1, 2, 3. And if we continue to apply the rule, we'll see it's actually recovering the slice of this slice for nilpotent Coulomb G2. And the top slice we see here, using the decoration we know is a G2, and which is exactly fitting to the cone of G2. And also another quiver, which this modification, the slide symmetry and union appears at the same time is this one is a Higgs branch of 1, 2, 4. So I will omit the middle steps. So this will be some non-trivial, non-minimal transition, and we will finally reach 1, 2, 1, 1, 1, 1. And there are 4 nodes undecorated. And here things becomes tricky because we know the next step we're going to do is we will subtract the D4 quiver. And there are in total 5 different choices of D4 in this case. So we can, of course, we can choose a D4 locally looks like this. So 1, 2, 1, 1, 1. We can choose locally a D4 with 3 nodes separated. Actually, here we have 4 different choices of this one. And also, we can have a D4 with all of the nodes, all of the U1 nodes separated. And here we only have 1 choice. And so the Hassen diagram corresponding to this will be, here it will be corresponding to a union of 4 G2. And here it will correspond to 1 G2.
How many nodes do you have? 5?
So there are 5 nodes here, and
So it should be 5.
and 4 of them are separated. So there are in total 5 different choices, but 4 of them
I see.
will be identified by the decoration.
Then will be identified.
So because
4 of them will have
Yeah.
3,
4 of them will have 3 decorated
and
nodes,
1 will
and
have
1 of
4.
them will have 4 decorated.
So they should be
So
different.
yeah, so the 4 of them should be identified through the decoration, which is a union of 4 G2. So like here, so this part you can choose this. This part will be corresponding to this single G2, right? And then these 4 G2 are corresponding to, you choose any of 3 decorated node here, and together with a node here.
Which slice in the 8 is this?
But this is actually in the new cone of F4,
In F4, but not E8?
not E8. E8 will be, if we choose 5 here, it will be E8.
Sorry, I don't understand this picture here. So you start with the H124.
Yeah,
You've done this algorithm, you've had some decorations.
Yeah.
And the decoration, would you have this S4 symmetry?
yeah. So maybe I can be more precise.
And then I don't understand what these slash G2 notations mean.
So
Why don't you draw the Hasse diagram without the quivers in between?
I can, yes. So
These little quivers there are supposed to be the label for these edges, one edge to the up to the left and
Yeah.
4 edges up to the right.
He's using the convention without specifying that the leaf label is a quiver.
Right. Yeah.
So I call this leaf as L1, and I call this leaf as L2, and this leaf as L2
You
prime.
don't, you just called it now.
No, I mean I call it, yes, I call it now. I call it now, yes. And as this as L, I don't know, L3. And L1 can be described by the quiver 1, 2, 1, 1, 1, 1. So we have 4 nodes, and with 4 of them separated. So I will label the node. I will give them a mark. I will give them a label, and I call it node 0. I call it node 0, and this one is node 1. This one is node 2. This one is node 3. This one is node 4. Okay.
Okay, yeah.
Yeah.
Starting to understand.
And because what I can do is like, because I'm trying to subtract the D4 from this L1. So I have 5 different choices. So this D4 have 4 U1 nodes. And
Right,
now I have 5 U1 nodes, so I have 5
I see.
different choices.
I see.
And if I choose, so this
4 of them
L2,
are all identified by
Yeah.
the symmetry,
Yeah.
and the other one is not.
Yeah.
Okay.
So this 4G2 will be, it will be a subtraction of necessarily contains this undecorated node, and maybe 1, 2, 3, so 0, 2, 3, 4, 0, 3, 4, 1, and 0, 4, 1, 2.
I see.
And this L2 will be corresponding to the subtraction. So this
I
two,
see. So your point was that,
yes, 1, 2, 3.
there were two different effects of the symmetry was producing. Some
Yeah.
saying that some leaves get identified, and some
Yeah.
saying that some type ADE singularities could be thought of as giving you a non-Michael Wall group
Yes.
for the larger singularity. In terms of this codimension 2 leaf, and now you're doing an example where both phenomena take place.
Yes.
Because all of these edges have this G2, so there's additional symmetry on them, which is a G2 non-Michael group for the bigger thing with respect to for the bigger leaf closure. And then also we have 4 of them, so we have a non-normal collection of 4 D4 singularities for that slice, but such that the non-Michael group gives you 4 copies of G2.
So what, the answer of the Higgs function, right?
You mean 1, 2, 4? Let me think. 1, 2, 3, 4. So what I'm gonna get from the end. 5. The symmetric, yeah, it's fine.
So what is the Hasse diagram?
The Hasse diagram will be, so actually, if I use a short notation, so here will be the symmetric product of the symmetric 4 of C2, and then above will be a G2 of 4 G2 and the A1. So the symmetric 4 of C2 looks like A1, A1, and 1, and A1.
But you started drawing the diagram of there.
Yeah.
But that's not the diagram, right?
Which one? You mean this?
Yeah.
This is the diagram from this leaf to the top. And the bottom is a symmetric 4 of C2. Because I want to discuss this effect, so I omitted the bottom. But overall, it looks like this, and it's a slice in the new cone of F4. Maybe I should write it down.
Are we supposed to know why it's a slice in the null cone for F1? It's just some magic here.
So actually it was calculated by so if you measured by the Hilbert series.
That's how you predict.
No, I disagree. Each time there is an orbit which has a canonical quotient equal to SL, you should have symmetric N of C2 as a subdiagram in the hypothetical code.
Yes.
That's the magic, if you want.
So say it again, every time you have what?
So every time you
use the canonical quotient,
Uh-huh,
if it's of type Sn,
uh-huh,
and we have the values 3, 4, and 5,
uh-huh.
then you should expect the Hasse diagram of symmetric N of C2
yeah
as a
as a
subdiagram.
subdiagram of the whole Hasse.
Okay. But a priori, there's no reason why we should be getting an interval, which is a quiver variety, yes, which is a Higgs branch of a unitary quiver in this.
And then, since there is a quiver for the symmetric of C2,
Right, and we'll get
which
it, that,
makes the form,
that appears in there, yes, of course, at least that much, right, okay. As long as you have, if you have a sim n of C2 as a slice, then I agree that. That is a
there is a
quiver,
quiver restriction for these slides.
Yeah.
but then you have to still be lucky, I'm guessing, to expect that to extend to a larger. Higgs branch of a unitary quiver. That is also contained, so in this case, it's not just the sim for C2, but it's something larger, which is appearing inside of nil one of it.
Yes.
Of the four, do you have a reason for that?
Yeah, if you only look at the symmetric 4 of C2, we should only have this 1, 4 with a loop. And then the top part, actually, we need to extend this quiver by.
But that's also the case. If you take 1, 2, n and the loop,
Hmm.
this should be, should have a Hasse diagram, which is a sub diagram in the corresponding.
Oh, this is an
Yeah,
enhanced
so, yeah,
statement.
That's what's happening here. So 1, 2, 3 is a slice in new G2. 1, 2, 4 with a loop is a new subgraph in neocomb F4, and 1, 2, 5 is in neocomb of E8. And we cannot, and 1, 2, 6 is no longer in the neocomb of any simple algebra because the canonical quotient for the neocomb of the algebra is S5 as the maximum. We don't have S6.
It's even stronger like this because these are Higgs functions.
Yeah, and also the corresponding Coulomb branch is dual, is also within the neocomb, and is exactly the dual part of the.
The strongest statement is what, sorry?
He just said it instead of this also.
Yeah,
Ah,
so for example, here, the neocomb of G2, what are you gonna look, it looks like, so G2, so this part is actually, I'm just write up, so C1, M1, and the small G2. So this part is the symmetric 3 of C2, and because here we have a free C2, so it's really silly. And the Higgs branch of this quiver are corresponding to from the minimal leaf to the top leaf, and the Coulomb branch of this quiver are the closure from the subregular leaf. So we can see a nice,
but the strongest statement in terms of the Higgs branch, because there's an additional statement for a Coulomb branch.
Yeah.
here. But the strongest statement for Higgs branch is when you have this A group being Sn, then you expect the Higgs branch of this 1, 2, n with a loop to be inside of the Hasse diagram. In other words, to be isomorphic to a slice of the closure of one leaf in another.
Yes.
Okay.
Yeah.
And yeah.
So both for Higgs branch, and for the Coulomb branch, you get it from taking one.
and here is modified.
And you
So-
have to be careful because some of those orbits are special, some of them are not
Yeah.
special.
So this one thing like, so I think is one possible way to just extend. So actually, Ben the Webster have a definition for special leaves, and I think for the quiver varieties, the extension of the special, which just encoded by the decoration. So we can see every time when there is a non-trivial decoration, the leaf is non-special. And also, we can also extend the notation of the Lucian's canonical quotient from the neocomb to a general quiver variety by looking at the decoration.
So whenever you have this,
Yeah,
then the special leaf will be the one that gives you this whole Higgs branch that you're saying. The other ones in between won't be special. Is that what you're
Yeah.
saying?
so every time when we have a non-trivial decoration, it will be a non-special.
Okay.
Do you have the precise orbits?
The precise orbit of which one?
F4 function, the Coulomb.
I have. Should be able to. Let me check. So. Right, bring stuff here. Yeah, and one more comment on this dn+1. So of course, we can also decorate this two with another decoration, but then this S2 cross S2 will also reduce it to a single S2 on the finite thinking diagram. So for general DN, you only you at the most you will have an S2, which fit with the thinking diagram of automates. Finite type. So for this quiver, the Higgs branch is equals to the Shortwave slice using the cone of F4 between the leaf of F4, the top leaf, and no, not sorry. F4 between F4 A2 and A2 plus A1 tau. And the Coulomb branch is a slice still within F4 between F4 A3 and A1 plus A1 tau. And for 1, 2 is 5 and the loop. It's in a new of E8. It should be the post.
This common notation you're using?
This notation of the slice.
So, Misha Finkelstein is using notation of Finkelstein.
Yeah.
Notation of token proton.
Yeah, because so in that case, it's specified algebra separately, and then he used a top and the bottom. So actually, I prefer Finkelberg's notation, but here we have too many different algebra to consider. So yeah, and we have to compare them. That's why we put the subscript as an algebra.
Well, I don't know how this is using this notation.
Well, this A2 plus A1 tilde, what does this mean? This is another.
Is a Balaka label for the leaf.
Neighbor for the leaf. Let's see. The F4 of A2 is indicating a leaf, right? And this A2 plus A1 tilde is not indicating itself a leaf, it's indicating how to get a neighboring leaf from the original. It is another leaf.
It's another leaf. It's a slice between the two leaves. So for example, for G2. Okay, so the G2, let me check the table. G2 have Balakata label as a top leaf labeled as capital G2. The subregular leaf labeled as G2A1. And the middle leaf labeled as A1 tilde. Here is labeled as A1. Here is labeled as 0. And then we can see the Higgs branch is a slice between G2 and A1. So this is what I mean. So because I take the slice between A1 and G2.
Mhm.
I think the Balakata label are somehow related with the parabolic subgroups. There's a Baroque subgroups and it's the parabolic subgroups, but I don't know how exactly this thing is derived.
Mhm.
It's kind of like which element nilpotent element it contains in which Baroque subgroup. And sometimes it's not necessary, so we need two. We need some more information, like it's just better on the Baroque subgroup is not enough.
Yeah, I mean, I guess it,
But what I really mean is like we take these two leaves and take the intersect the slice in between.
yeah, you intersect the slice to the small leaf,
Yeah,
with the closure of the larger leaf.
Yeah.
That's what you mean. We could think about it all in terms of just the closure of the larger leaf if we wanted to. Then it would just be the slice to this. If we restrict it to the closure of the larger leaf, we'd just be taking simply the slice, the smaller leaf. The notation looks a little bit complicated this way.
Yeah, I when Paul was visiting, I complained to him about this Balakata labels.
yeah,
He was,
but we don't have a better way.
he wasn't accepting.
Well, there is a better way.
What's
Do the characteristics, so actually, we know what they mean. We don't know what data they mean, we know that they exist. So the dictionary between the two, which you can get out of.
So what's your label? So for example, in this G2, would you want to label as?
That would probably be 1, 0. And then we do 2 labels, 0, 0, bottom 1, 0,
Ah,
0, 1.
I see.
0, 2.
I see.
Yeah, we could use the Lincoln label.
You're using the Lincoln label.
If you know what it's
Yeah,
mean.
but do you also use, how do you denote the slice? An intersection of the slice with the code?
It's a good question. I mean, I think, I don't know if I fixed a single notation for it, but yeah, with S or whatever, something for the slice. And then you could do a subscript. For example, of the leaf you want to take a slice with, and then you can intersect it with closure of another leaf. This would be one possibility.
This is the notation used in the intersections paper, except the linking labels.
Yeah, so the difference with the interval is that you have in the notation, you have the top and upper and lower.
That's what these things are.
Superscript.
No, it's not, but if we were doing it that way, then we could just get rid of this F4 EA.
Get rid of
And
it.
just, I guess the reason why, if I understood it right, Deshuo is doing that, because there's a concern that
Yes.
maybe
because
some of
I
these
did-
Balakata
Yeah.
labels could be used for more than one nilpotent column.
Exactly.
So in order to specify which one, he has a superscript telling you which
Yeah.
one.
Yeah, so I'm basically like,
something like-
algebra and
One could just do S sub L1 super L2 or.
Yeah.
or
that's a
Yeah,
much more
that's-
common notation.
That's what.
One could do it that way. Maybe technically it would be SL1 super L2 closure or vice versa, whichever one is bigger.
Yeah.
Yeah. Because you really take a leaf, a small leaf and a larger leaf closure. You take the slice, the smaller leaf inside of the larger leaf closure. The small leaf is contained in the closure of the larger leaf. All leaves themselves are disjoint and smooth, but the small leaf could be contained in the closure of the larger.
Yeah, so the order doesn't actually matter.
Yeah, the whole thing wouldn't matter, except here we need it because the notation might be ambiguous otherwise.
Yeah, So.
Of course, it could also be, right, not that it's necessarily a problem, that even if your original nilpotent from, of course, the nilpotent cones and the quiver varieties and the Higgs branches of unitary quivers are all normal. Of course, a leaf coder doesn't have to be normal, so then you have this issue as well, but you could ignore it.
So, right.
Do you want to take a break?
Yeah, you want to get lunch?
Everybody happy to go there? Yeah.
Okay, so let's thank Deshuo. Are there any questions before we break for lunch?
You were asking about the geometric interpretation.
Of
Yeah,
energy.
yeah.
Yeah.
Like so what do you consider as a geometric?
Any answer that uses algebraic geometry is not physics.
So
How do you see that it's normalized next to C2, for example?
So actually because the last rule we got is like, for example, 1, 3, G, and it breaks into 1, 1 with the loop and 2 with G loop, and there are 2G minus 1 in between. So in this case, if we're trying to find the normalizer of this U1 cross U2, quotient by itself within U3. So what we have will be just a trivial group. And so we will naturally expect there is a C this will just be some free module C with dimension 2. Yeah, but actually it's not the case. So this normalizer is only telling you the information of the normalized slice. It will not tell you what was so if it's non-normal, it's no longer gives you the precise slice. But you can think of it this way, like you can think of this stuff as so we have let me think. I just put it at n and so we am syncing, but I'm not sure if it's
Actually, I didn't realize that we were supposed to have a correspondence between normalizer of some tori and the singularity itself. Like we're not supposed to read in general the singularity off from just the information of normalizer.
Yeah. So for example, here we have n coordinate, and each xi I will actually see it represent a C2. No, a C2G. Sorry. And yeah, and this there is action of group action Sn. So what I'm really doing is that so because here the G, so the loop is in the adjoint representation of UN, right? It's actually another, it's adjoint plus the dual of the adjoint, which actually dual of the adjoint is adjoint. So in this case, and so the action of UN can be reduced to the kata, right? And for the kata, it is just a well action of action. Okay.
This is the case where you have just a single loop.
Yeah, but
you wrote a G there, you meant.
yeah, and
G
here.
loops, or the G means the G loops, the G you have in the diagram.
Sorry, here no.
Just a single loop.
Here is G and here is the algebra G.
Right.
Yeah, so that's the case for the single loop. And
so if the Roman G is 1,
yeah, maybe I should
then we get, so in general we get G plus G star to the Roman G times.
Yeah, like
if the Roman G is 1, we can reduce it to H plus H star minus.
Yeah. And here I think for the for G loops, where Deshuo can do the similar stuff, not precisely the same, but you can also think of here there are like G copies of the Catan. Because the thing that
Well, this is not.
yeah, this is not let's think
How
about
do
it.
you define this loyalty?
This is
But
right.
the thing is like, so the part from the Catan, everything are already contained here.
This variety is closely related, so
Yeah.
this is maybe a subject for a later discussion, but this Roman G can be analogous to the genus of a surface, a Riemann surface, and you would look at the character variety to the moduli of rank and local systems on it, or a GLN or SLN, whatever bundles on it, and that will be closely related, not exactly the same as this variety here. But when little g is 1, then we're just getting something that looks like a commuting variety, and it's going to be so if you have pairs of commuting matrices after simultaneous conjugation, then that's just classified by their eigenvalues, but their eigenvalues up to simultaneous commutation, but you can diagonalize both of them simultaneously.
So maybe here,
Then you
yeah.
get this Sn group acting on C2n. And that's why this H plus H star mod Sn occurs. So when the Roman G is bigger than 1, I don't have such a description in general. I mean, you can describe it just literally, but I don't have such a reduction to the Cartesian description.
So yeah, so maybe if we just look at a single loop, this reduction is legal, and then it's a 3 copies of C2 quotient by S3, and
Exactly.
so this N, you can think of like if you took the fixed loci of one of the S2 action, and then here like you will kind of like looks like you are doing a S3 action, the quotient, but there are two inequivalent parts, like so because the Hassen diagonal looks like this is a fixed loci of S3, this fixed loci of S2, of S1, and if you take any S2 here, like for example, we have C2 or C2 or C2, then we already identified this 2C2, but then we still we're trying to take S3 quotient over the whole thing, but we already identified 2 of them. So it looks like a mismatch, and when this mismatch happen, we kind of expect the non-normal slides. That is the way I'm thinking of it. I don't know if it's.
That's the sort of answer I was looking for, yeah, the question of even rank 1 is interesting.
Yeah. Here is M1. Here is.
So basically, if the Roman G is 1, and we're just looking at a single loop, then it turns out to be just a finite group of quotient singularity. And so in that case, we can talk about these normalizers and stuff, and try to understand what the singularities are, and well, at least get the normalization of the singularities this way, but then you can get something non-normal.
So when it's no longer one loop, it's G loop, this reduction is no longer true. But however, the stuff entering the transverse slice is still takes value in the Catan, not in the whole algebra. So this can be worked out by the Higgs mechanism. So still we can use a similar way of thinking, but the reduction is no longer true. But the transverse slice is still like take value in the Catan.
Transverse slice contains value.
It takes value in the Catan.
For just the nearby, the neighboring.
You can think of the transverse slice are actually the trees of the UN.
Right, because the neighboring slices have to be one of these 3 types that you've had. All right, any other questions? Okay, so we'll get lunch, and we might have someone here in 20 minutes, so be aware that, or maybe even less than that, so be aware that we might have to move to another room to eat our lunch.